You will measure the wavelengths of the lines of the visible portion of the hydrogen spectrum and then compare them to the values calculated by the Bohr model. We're going to use a spectroscope. This is the one that the maker of this PowerPoint, Mr. Mike Jones, has at his high school in North Carolina. We have a similar one, although you will be using some ones that were made for astronomy. You use it to measure the wavelengths of the lines in the atomic spectra. The way that it works is that you apply a high voltage to a narrow tube filled with hydrogen gas and it glows. You get a light. That light is then viewed by looking through a diffraction grating which separates the light into its components. You see the yellow circle around the eyepiece. When you look at it, there is a screen, and the spectral lines produced by that screen actually will show up. The light passes through a slit, and then the spectral lines appear superimposed over the scale so the wavelengths can be determined, and those are 3 lines from the hydrogen spectrum. And you would read the wavelengths in 10 to the minus 7 meters. This is an actual photograph of the light coming from the spectrum tube, and you can see the lines on the diffraction grating, and you can actually measure them. This is an excellent, excellent photograph made by Mr. Jones about 7 years ago. What you then have to do is predict the wavelength of the light emitted as the electron moves from a higher energy level to a lower energy level. What I'm going to do is give each group an energy level where it starts and where it ends, and you get to do the calculation. Bohr's equation can be used to predict the energy of each allowed energy level or energy state for the electron, where n is the energy level number, r is Rydberg's constant, and you simply put the values in. N will have a value of 1 through 7. Rydberg's constant, 2.18 times 10 to the minus 18th joules, makes all of this work in joules. That's not a number you need memorize. What you then do is, having calculated the energy of an initial and a final state, as you subtract them, you get the change in energy. You can then use the equation we have for change in energy to calculate a wavelength. And this wavelength will come out in meters, which is the reason that I suggested you leave your wavelengths as 10 to the minus 7 meters.